Hello, everyone. I hope everyone is doing okay. This video is for chapter 4. It might be a little longer than usual. This is a long chapter. So let's get started. So chapter 4 deals with probability. A probability is a measurement of how likely an event is. And for 4.1, the basic way of calculating probabilities is by calculating a quotient. Okay, the numerator is going to be the amount of uh, outcomes we have for a specific event, and the denominator is going to be the total amount of possible outcomes. So we're going to practice with this question number 3. What is the probability of rolling a 4? Well, that would be 1/6. Because on a die, you have 6 different options, and we only care about one of those, which is number 4. So let's calculate this. We want to round to 3 decimal places. 0.167. Good. For the second one, find a probability that when a coin is tossed, the result is tails. Again, we have two possible options, heads or tails. We care only if the result is tails, so 1/2. This is 0.5. And lastly, the probability that when a 6-sided die is rolled, the outcome is 21. So this is important. Remember, whenever something is impossible, then we are on one side of the spectrum, that is 0. And the opposite is when something is certain. So you're gonna get a couple of questions like that on the assignment and on the quiz and on the midterm. So whenever something is impossible, the probability is 0. Whenever something is certain, the probability is 1. Okay, let's move on to question 12. It is impossible to get 9 queens when selecting cards from a shuffled deck. Express the indicated degree of likelihood as a probability value between 0 and 1 inclusive. It is 0, right? Key word here is impossible. Something cannot occur. Probability is 0. Question 14. Refer to the sample data for polygraph tests shown below. If one of the test subjects is randomly selected, what is the probability that the subject is not lying? Is the result close to the probability of 0.42 for a negative test result? Consider the result close if the absolute difference is less than 0.050. So the probability that a randomly selected polygraph test subject was not lying is, again, we construct a probability. We want a quotient. The numerator is going to be the amount of subjects who did not lie. We can get that from this column, 13 plus 32. And we divide by the total amount of subjects in this experiment. So that would be 13 plus 32 plus 45 plus 10. So if we simplify this, we would get 45 over 100. So this is 0.45. And is the result close? They are telling us that for it to be close, the absolute difference has to be less than 0.050. So let's calculate this absolute difference. Remember, difference means subtraction. And absolute means we want it to be positive. So let's subtract 0.45 minus 0.42. The result is 0.03. Is 0.03 less than 0.05? Yes. So yes, because there is less than 0.05 absolute difference between the probability of a true response and the probability of a negative test result. I hope we're good so far. Let's move on to question 17. On their first date, Kelly asks Mike to guess the date of her birth, not including the year. Complete parts A through C below. What is the probability that Mike will guess correctly? So we only have one birthday out of 365 days in a year. Notice we are asked to leave this as a fraction. So we always have to pay attention to how they want us to present their answer. We could have a decimal, a fraction, or a percentage. And notice we ignore leap years, so it's only 365. Would it be unlikely for him to guess correctly on his first try? No. If we approximate this as a decimal, that's 0.0028. That means that it's less than 1%. So it is not likely. It is unlikely for Mike to guess correctly on his first try, as the probability of a correct guess is very low. So it is not likely. It's not impossible either. So it is unlikely. And lastly, part C. If you were Kelly and Mike did guess correctly on his first try, would you believe his claim that he made a lucky guess, or would you be convinced that he already knew when you were born? Mike already knew, as the probability of a correct guess is very low. And this is very important. This is the foundation of what we're going to do in upcoming chapters. We're going to try to use this low probability so that if we have a hypothesis and the probability of our hypothesis being incorrect is very, very low, we will conclude that our hypothesis is correct. So this is important. This is what we're going to use probabilities for in the future. Okay, we have one more example in question 20. Each of two parents has the genotype red-brown, which consists of the pair of alleles that determine hair color, and each parent contributes one of those to a child. Assume that if the child has at least one of the red ones, that color will dominate and the child's hair color will be red. List the different possible outcomes. Assume that these outcomes are equally likely. So this is important. Remember, we have a name for this. The set of all possible outcomes is the sample space. And something important is we need to consider every possibility. So we could have red and red, we could have brown and brown, or we could have a combination. But notice that it's not the same to have red-brown than to have brown-red. So always list all possibilities. Part B, the probability that a child of these parents will have the brown-brown genotype is 0.25. How do we know this? Because we have four possible outcomes. That is the amount of outcomes in our sample space. And in only one of those, the genotype is brown-brown. So it has to be 0.25. And what is the probability that the child will have red hair color? So we are being told that if the child has at least one of these red alleles, that color will dominate and the child's hair color will be red. So how many of these four possible outcomes have at least one red allele? So this is red, this is one, red-brown, this is two, brown-red, this is three, and brown-brown does not have a red one. So we have three possible outcomes where we have a red one. So the probability is 3/4. which translates to 0.75 as a decimal. Yeah, I hope this is clear. Let's move on to some examples from section 4.2. 4.2 review. So in 4.2, we have two rules that are important. Those are the addition rule and the multiplication rule. So I think this is a split. I think 4.2 day one deals only with addition rule, and then we're going to work with multiplication rule on the next assignment. So let's do question 9. We're going to have a lot of these tables. So let's see how we can use these to find probabilities. Use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assume that orders are randomly selected from those included in the table. If one order is selected, find the probability of getting an order from restaurant A or an order that is accurate. Are the events of selecting an order from restaurant A and selecting an accurate order disjoint events? So first of all, we find the probability. We can do this using the addition rule. We would need to find the probability of getting an order from restaurant A, then find the probability of getting an accurate order. We add them, and then subtract the probability of getting an accurate order from restaurant A. What I suggest we do is we simply use the table. So in how many of these 8 boxes do we have either an order from restaurant A or an order that is accurate? Well, this first one, 311, that is both from restaurant A or accurate. So we consider that. This 261, that is accurate. This 239, that is accurate. This 150 is accurate. And this 39 is not accurate, but it is from restaurant A. So we also consider it. Remember, we want either from restaurant A or accurate or both. That's the numerator, and the denominator is the total amount of orders that we can choose from. So that is the total. So that is 311 plus etc. until 15. So let's calculate this. 311 plus 261 plus 239 plus 150 plus 39. That is 1,000. And on the denominator, we have that plus 50 plus 33 plus 15, which is 1,098. So if we calculate this quotient, we would get 0.911 rounded to 3 decimal places. I suggest you do that. If you prefer to use the addition rule formula, that is also correct. So you do the way you think it's easier for you. And then are the events of selecting an order from restaurant A and selecting an accurate order disjoint events? The events are not disjoint because it is possible to receive an accurate order from restaurant A. So remember, disjoint means that if one occurs, automatically the other one cannot happen. Okay, so these two are not disjoint because it's possible for both of them to happen simultaneously. It is possible to receive an accurate order that is also from restaurant A. So if it's possible that both can happen simultaneously, then the events are not disjoint. Okay, let's move on to question 11. Use the following results from a test for marijuana use, which is provided by a certain drug testing company. Among 141 subjects with positive test results, there are 29 false positive results. Among 158 negative results, there are 2 false negative results. Complete parts A through C and construct a table. So let's do that. Let's construct a table. I'm going to use Excel for it, but you can do it with a notebook, like you can write it down. So we have 2 possible categories. We have used drugs or did not use drugs. And we have positive test result or negative test result. So we are told that we have 141 subjects that have a positive test result. Let me see if I can make this a bit smaller so that we can read that information. There we go. So we have 141 positive test results, and out of those, 29 are false positive. What does that mean? It means that the result is positive, but they didn't use drugs. That's why it's false positive. So we have 29 subjects in this category. These got a positive test result, but they didn't use drugs. We are also told that we have 158 negative test results. Those go here. And there are 2 false negative results. What does that mean? It means that the result is negative, but it's not correct. So that means that they did use drugs. So those 2 go here. These are false negative test results because the tests say they didn't use drugs, but they did use drugs. Now, how do I know how many true positive results we got? Well, I know we have 141 total and 21 didn't use drugs. So if I subtract that, I can find how many did use drugs, which is 112. And by the same logic, if I know that I have 158 negative test results and 2 of those used drugs, the rest didn't use drugs. So we were able to construct our table. Now let's use this to find our probability. Okay, so first we are asked the total number of subjects in the study. We can simply add these two, 141 plus 158, 299. How many subjects did not use marijuana? Let's take a look. Didn't use drugs. We can add these two. 29 plus 156, 185. And what is the probability that a randomly selected subject did not use marijuana? So we know this basic concept of probability. I want a quotient. The numerator is the amount of subjects who did not use marijuana, which we know that it is 185 from the previous question. And we divide this by the total amount of subjects, which is 299. So this is 0.619. Do not round to the final answer up to 3 decimal places. Perfect. So this is a simple table exercise. We're going to do a lot of these, but I wanted to show you how to construct these tables. We need to be careful whenever we have false positive and false negative test results and get them in the right position on the table. Okay, I think that's all for question. No, I mean for this section. Sorry, I forgot the word. I want to show you a couple of examples from the next assignment, which is 4.2, 4.30. I stopped sharing. Let me share my screen again. There we go. So let's work on question number 2. Yes. So here we have another table. If 2 orders are selected, find the probability that they are both from restaurant D. But now we have 2 different experiments. The first one is with replacement, and the second one is without replacement. Remember, this means that when we're taking the orders, like let's select the first order. Imagine we have all the orders in front of us. We can select one, we can pick it up. So we have one less order than we had before. So with replacement means I put it back. So the second time I choose an order, the conditions are exactly the same as when I chose the first one. Without replacement means that I take the first order and I don't put it back. So now I have less options to choose from. So let's see how those two compare here. Assume that the selections are made with replacement. Are the events independent? The probability of getting 2 orders from restaurant D is, using the multiplication rule, let's first find what is the probability of getting an order from restaurant D. How many orders are there from restaurant D? I have 146 that are accurate and 13 that are not. And then I simply divide by the total, which is adding all the 8 boxes. So let's calculate this first. 146 plus 13, that is 159. And then the total is 1099. So if we calculate this quotient, we would get 0.145. We would get more decimals. Let's just stay with this. I just read that we should not round until the final answer. So let's just stick with this fraction for the moment being. It is 159 over 1099. So this is the probability of selecting one order from restaurant D. Now we want to select 2. So we multiply this by the probability of selecting one order from restaurant D. Notice this is with replacement. So I took one of the 159 orders, but I put it back. So I still have 159 to choose from. And the total is still 1099. So if we multiply these two numbers, we would get 25,281 over 1,207,801. And now we can calculate this quotient, which is 0.021. Now, the events are independent because choosing the first order does not affect the probability of the choice of the second order. Now, something went wrong here. Let me check my math really quickly. Restaurant D, 241 plus 30 plus 267 plus 54 plus 314 plus 4. Yep. 9/1099 squared 0.021. Hmm. Oh, okay. I did not read the instructions. We are asked to round to 4 decimal places. So we did everything right. I just didn't round correctly. So important to always read these to get the right answer. Okay, so now part B, same thing, but now we are doing it without replacement. So the probability of selecting the first order from restaurant D is still 159 over 1099. And we want to multiply by the probability that the second order is also from restaurant D. Now, this is without replacement. So that means that I already took one of the 159 orders. So I only have 158 left. And I don't have 1099 orders total anymore because I already took one of them and I didn't put it back. So I have 1098 orders left. So let's calculate this. Rounded to 4 decimal places. This is 0.0208. And now these events are not independent because choosing the first order affects the probability of the choice of the second order. By not replacing the first order I took, the probability for the second order changed. So that's why these are not independent. Okay, let's move on to question 8. The principle of redundancy is used when system reliability is improved through redundant or backup components. Assume that a student's alarm clock has 9.2% daily failure rate. Complete parts A through D below. What is the probability that the student's alarm clock will not work on the morning of an important final exam? So we are being told that's 9.2. That is a percentage, and we want a decimal. So we divide by 100, and it is 0.092. If the student has two such alarm clocks, what is the probability that they both fail on the morning of an important exam? So these two alarms are independent. So we know that by the multiplication rule, we multiply these two probabilities. So that would be 0.092 times 0.0092, which is 0.00846 rounded to 5 decimal places. And what is the probability of not being awakened if the student uses 3 independent alarm clocks? Same principle, I have 3 independent alarms. So I multiply the probability for each one of them. And this represents the probability that none of those work, that all of them fail. So that is 0.092 cubed, rounded to 5 decimal places, 0.00078. And basically, we can analyze what happens. Notice that by adding one more alarm clock, the probabilities that all of them are going to fail decrease considerably. So that's basically what this principle of redundancy is used for. So let's take a look at question at part D. I mean, do the second and third alarm clocks result in a greatly improved reliability? Yes, because total malfunction would not be impossible, but it would be unlikely. And again, that is being represented by how much these probabilities decrease. They decrease by a lot. Okay, let's take a look at question 21. In a certain country, the true probability of a baby being a boy is 0.537. Among the next 7 randomly selected births in the country, what is the probability that at least one of them is a girl? Now, this is kind of like a hard question in the sense that if we just try to do it straightforward, it would take a lot of work because we would need to find the probability that we have exactly one girl and then add it to the probability that we have exactly 2 girls plus the probability that we have exactly 3 girls and so on. And that takes a lot of work, a lot of time. So what we do is we use the complement. So what is the complement of this event? The event of having at least one girl. Remember, the complement is the opposite. So if my first event is having at least one girl, the opposite is having no girls at all. And how do these two relate? Remember, the addition of these two probabilities is equal to 1. So if I find one of these probabilities and I subtract it from 1, I can immediately get the other. So that's what we're going to do. We're going to find the probability that none of the babies are girls and then subtract it from 1. So this is 1 minus the probability that all of the babies are boys. And how do we find that probability? We're selecting 7 babies, and the probability of each one of being a boy is 0.537. Remember, by the multiplication principle, that means that I need to multiply each one of these probabilities. How many of these am I multiplying? I'm multiplying 7 of them. So this is the same as 0.537 raised to the 7th power. Remember, we are subtracting these from 1. So this is the same as 1 minus 0.537 raised to the 7th. That is rounded to 3 decimal places, 0.013. That is 0.989. And it makes sense, right? Like if seven babies are born and basically half of the probability is of those being girls and half of being boys, we would expect that at least one of them is going to be a girl. So that's why this probability is very, very high. And remember, the key of this exercise is using the complement. We could have correctly found this probability by finding all the smaller probabilities, but that takes a lot more work. So let's not do all that extra work and do it in a more efficient way. And I have one last example I want to discuss in this assignment is 29. In an experiment, college students were given either 4 quarters or a $1 bill, and they could either keep the money or spend it on gum. The results are summarized in the table. Complete parts A through C below. Part A, find the probability of randomly selecting a student who spent the money, given that the student was given 4 quarters. Now, this is a conditional probability. The key word here is given. Whenever we see that given, that means this is a conditional probability. We have a formula for this. The probability, let me see if I can write it here, of A given B is the same as the probability of A and B over the probability of B. So basically what this means is we want to find the probability of A, but we have a bit more information than we had at the beginning. That's what basically a conditional probability is. And we can find it using this formula, but also we can find it using the table. How can we find it using the table? Let's take a look. It will be a quotient. We know a probability is represented by a quotient. What is the probability that a student spent the money and was given 4 quarters? How many of those students do we have? We have 29 of them. These 29 were given 4 quarters and spent that money on gum. So that is 29. But notice that now I am not going to divide by the total because I don't care about the students who were given a $1 bill. I know I'm not selecting from those students because I'm being told that the student I'm going to select was given 4 quarters. So that means that I only focus on the first row. So this is 29 plus 13. So if we calculate this quotient, we would get 29 over 42, which rounded to 3 decimal places is 0.69. Find the probability of randomly selecting a student who kept the money, given that the student was given 4 quarters. So this is pretty similar, but now we are interested in the students who kept the money. There are several ways of doing this. We could use a formula. We could do what we just did, or we could also use the complement. But let's do the same thing we did to just practice a little bit more. So I'm interested right now in the students who kept the money and were given 4 quarters. How many of those do we have? We have 13 of those. But again, I'm not going to divide by the total because I really care about the students who were given $1 bill. I know I'm not selecting from those. I'm only selecting a student who was given 4 quarters. So I only focus on the first row. So we would get 29 plus 13. And that would be 0.31. Rounded to 3 decimal places. And what do the preceding results suggest? A student given 4 quarters is more likely to have kept the money. A student given 4 quarters is more likely to have spent the money than a student given a $1 bill. And again, notice I mentioned the complement before because notice that these two are complements. We only have 2 options. So they either kept the money or spent the money. So these are complements because they are opposites. So we could have also found this 0.31 by subtracting 1 minus 0.69. You will find that there are a few correct ways of calculating probabilities. So you do the one that you feel the most comfortable with. Okay, I think that's all for this assignment. I'm gonna stop sharing for 1 second. And I want to do a couple of problems from the last assignment. which is 4.4. So let me share my screen again. There we go. Okay, so section 4.4 is called counting. And why are we doing this? Because sometimes to find probabilities in the denominator, we want the total amount of ways something can happen. So basically, this is what we're learning in section 4.4. So let's start with question 3. In a horse race, a particular bet is won if you selected the 3 horses that finish first, second, and third, and they can be selected in any order. A certain horse race had a field of 12 horses. What is the probability of winning this bet if you randomly select the horses? So this is a permutation. How do we know this? Because first of all, it is without replacement. How do we know that this is without replacement? Because the same horse cannot be first and second at the same time. So if we already select a horse to be first, we cannot select that horse to be second. So it is without replacement. And the order matters because it's not the same that our horse wins first place than if it wins third place. So order matters, and this is without replacement, so this is a permutation. And what is the formula for a permutation? That is n factorial over n minus r factorial, where n is the total amount of objects we can choose from, and r is the amount of subjects we are choosing. So this becomes 12 factorial over 12 minus 3 factorial. And if we simplify this becomes 1,320. Now, notice this is the total amount of ways we can choose the horse. And as I suggested before, this is going to be the denominator of our fraction. So what is the probability of winning this bet? Well, we are selecting one correct order out of 1,320. If we round this to 5 decimal places, we get 0.00076. Okay, I missed something very important. We are told they can be selected in any order. So this is not a permutation, this is a combination. Give me 1 second, please. So since this is without replacement and the order does not matter, this is a combination. And we know that the formula for a combination was that we just saw, n factorial over n minus r factorial. It starts the same, but we have an extra factor in the denominator. So this is 12 factorial over 12 minus 3 factorial times 3 factorial. So this would be 220. And again, this is the denominator. So we divide 1 by that, which in turn gives us 0.00454. Went. Okay, let's see What is going on here? Three. One over 220. 0.0045. What's 5? Okay. So let's review this since there were a couple of mistakes on the way. First of all, we know that this is a combination. How do we know that? We need two conditions. The first one is this is without replacement. That is because the same horse cannot finish second and first at the same time. And this is a combination because the order does not matter. How do we know that? The problem is telling us they can be selected in any order. So if we select the three horses in either order, as long as they are top three, we are winning this bet. After we do that, we use the formula and round correctly and get our result. Okay, I hope this was clear. I didn't. So let's move on to question 7. When testing for current in a cable with 6 color-coded wires, the author used a meter to test 3 wires at a time. How many different tests are required for every possible pairing of 3 wires? So again, we need to choose if this is a permutation or a combination. Those are the two common ones. We have a couple of different cases, like when we have a permutation, but we have more than one item. I mean, we have identical items that we can choose from. There's a different formula for that. That's on the notes. But in general, we will either use combinations or permutations. So here, this is without replacement because we cannot select the same wire twice. For this test, we are selecting 3 wires at a time. They are 3 different wires. And the order does not matter because we are taking 3 at a time. So if I select green, red, and yellow, or if I select yellow, green, and red, those are the same 3 cables. I'm grabbing them at the same time. So the order does not matter. So this is again a combination. So we use the formula for combination, 6 factorial over 6 minus 3 factorial times 3 factorial. So this is 20. And there is one last one I want to show you from this section, which is 13. So a corporation must appoint a president, a CEO, and a COO, and a CFO. It must also appoint a planning committee with 3 different members. There are 12 qualified candidates, and officers can also serve in the committee. Complete parts A through C below. How many different ways can the 4 officers be appointed? Okay, first of all, let's see if this is a combination or a permutation. Notice this is without replacement because we cannot have the same person be the president and the CEO. And notice that the order matters because if I select John first and Mike second, that means that John is president and Mike is the CEO. If I select Mike first and John second, then Mike is president and John is CEO. So in this case, order does matter. If order does matter and it is without replacement, this is a permutation. So this is the formula we had initially. In this case, we are selecting from 12 possible candidates. And we are selecting 4 of those. So this is 11,880 to appoint the 4 officers. Now, how many different ways can a committee of 3 be appointed? And notice that the officers can also serve on the committee. So that means that we're still choosing from 12. We are choosing without replacement, because if we choose Mary to be in the committee, we cannot choose Mary again. We need 3 different people, 3 different members. And order does not matter. On part A, order mattered because whoever I selected first was president, whoever I selected second was CEO, and so on. On part B, the first person I select is a member of the committee, and the second person I select is also a member of the committee. So those positions are identical. So the order does not matter. That means we have a combination. So if we have a combination, we use that formula. So this is 12 we are choosing from. We are choosing 3. And we have the extra 3 from the formula. So that would be 220. Excellent. And now, what is the probability of randomly selecting the committee members and getting the 3 youngest of the qualified candidates? So this is a probability, as in section 4.1, it's a quotient. Out of all the possible 3-member committees we can form, there is only one that has the 3 youngest qualified candidates. And how many possible committees can we form? 120. And we are being asked to leave this as a simplified fraction. So that's it. I'm not sure how long this is. I cannot check the time. This might be a little long. I hope you didn't get overwhelmed by this. There are a lot of topics in this chapter. Let me stop sharing. So please, if any of this was not clear, please reach out. I will be happy to help. Remember, we also have SI sessions, and you can also sign up for one-on-one tutoring. So we have resources that you can use if you feel like you're struggling. Okay, so that's all for now. Have a good one.